Hello, my name is Joseph Fassbender. This is the fall 2019 semester of CS 6263, and today I am presenting on real-time evasion attacks on deep learning-based anomaly detectors. First, I would like to make some acknowledgments to the authors of the paper being presented. From the CISPA Helmholtz Center for Information Security are Alessandro Erba and Nils O. Tippenhauer. From the Singapore University of Technology and Design are Riccardo Taormina and Stefano Galilei. From the Politecnico di Milano are Marcella Pagliani, Michelle Carminata, and Stefano Zanero. And here we have the original paper link PDF. As we have learned throughout this course, computational and physical infrastructure is very connected and dependent on each other in today's world. As a result of this, integrating security into industrial control systems has been challenging. With the advancements in machine learning, researchers have begun to explore how adversarial machine learning can be used to test and strengthen anomaly detectors. Evasion attacks have become a major threat, and attacks have evolved to replicate expected dynamics of a cyber-physical system, and attacks must be consistent with current system dynamics. So adversarial machine learning is being used to create these evasion attacks on top of cyber-physical systems with machine learning detectors. The purpose of this research has been to expose different types of threats to cyber-physical systems, as well as to illustrate how different types of attacks can persist through the use of adversarial machine learning. In this research, the authors create different types of adversarial attacks to evaluate anomaly detection systems on cyber-physical system datasets. The anomaly detector systems have learned the inputs and outputs of normal operating conditions, and the authors use different types of machine learning approaches to evaluate these systems and illustrate how easily they can be manipulated in a real cyber-physical system. We will begin with some background on what exactly an evasion attack is. These are attacks that occur going undetected by the system. In other words, the attack is being executed. However, the system has no idea it is being manipulated. In the world of adversarial machine learning, the goal is to go undetected by the machine learning detection software of the system. In these types of attacks, the attacker must manipulate the system to go undetected or otherwise have the system think that no attack is occurring. Therefore, system data is manipulated to be normal data and passed back to the sensors as normal data to cover the attack while the attacker manipulates actuators of the system. Here, the authors model an evasion attack where the attacker manipulates readings from the actuator to provide the SCADA with what the system expects, hiding the attack in the process. By doing this, the attacker could cause a system, such as a water tank system, to overflow while outputting regular readings. So the system would not see that an attack is happening, and the attack would have to be physically identified. And you can see here the attacker inserts himself kind of as a man in the middle of attacker between the PLC and the SCADA, taking those sensor readings and manipulating them to normal readings to the SCADA. The main types of attacks discussed in the paper include the white box attack, the black box attack, and the replay attack. In the case of a white box attack, the attacker is aware of the system model as well as system variables and thresholds. This allows the attacker to create a program to manipulate the system from the beginning and start an attack. Therefore, as soon as an attacker inserts themselves into the system, they can begin attacking. In the case of the black box attack, the attacker is aware of only the detection scheme, but not system variables nor system thresholds. This allows the attacker to hide itself while learning about the system. So the attacker inserts himself, and there is a learning phase where the attacker learns about normal expected data within the system. After the learning phase has commenced, the attacker can execute its attack on the system. The replay attack is a little simpler. The attacker will record sensor readings for a given time, and when the attacker is ready, it will simply repeat these readings while attacking the system. This allows the attacker to manipulate the physical controls of the system while outputting previously recorded normal readings. Here, the authors model the white box attack. The attacker takes data from the PLC. They then modify it and execute the attack. If the machine learning detection system within the system detects any of the modified data as potentially anomalous, the attacker will modify data further to avoid detection. In this scenario, again, the attacker can immediately begin attacking the system upon inserting itself. Here is a breakdown of the black box attack. As we discussed earlier, the attacker is not able to manipulate the system immediately and must begin with the learning phase of the attack. During the learning phase, the attacker takes in normal data to learn how the PLC operates and what sort of readings and threshold and what sort of readings the SCADA expects from the PLC. After the learning phase has completed, the attacker enters the attack phase, in which the attacker begins to manipulate the system and send back learned data to the SCADA. In order to evaluate the author's different types of attacks, two different data sets were used. The first dataset is known as Batidol, and it was originally used for modeling the hydraulic response of water distribution systems to cyber-physical attacks originally generated for the Batidol competition. The second set of data that was used by the authors was the WADI dataset, which was originally based on a water distribution testbed at Singapore University of Technology and Design. Both white box and black box methods were implemented with Python version 3.6.5, and both autoencoder and convolutional neural network methods were used for the machine learning aspect of this research. The attacker was trained on sensor readings during normal operation and during attack phases. The authors launched white box, black box, and replay attacks on both sets of data for evaluation. The following table represents the detection accuracy of the anomaly detector in an unconstrained attack, where attackers have access to all sensor readings in the system. Within the Batidol dataset, it was found that the replay attack goes undetected completely, while the black box attack is detected with an accuracy rate of 0.14. The black box attack is detected at a rate of 0.14 while using the autoencoder method, and 0.27 when the convolutional neural network method is used. In comparison to the WADI dataset, the replay and white box attacks are detected at the same rate, and the replay attack is not completely hidden in this case. The black box attack is detected at a higher rate for both the autoencoder and convolutional neural network methods, while the autoencoder method is detected at a slightly less rate. Another attack that was used was a constrained attack. In this case, the attacker is only given a certain number of features it is allowed to modify within the system. For the replay attack, in the case of both datasets, as the constraints increase, the detection accuracy also increases. Therefore, as the replay attack loses access to more sensors, it is more likely to be detected by the anomaly detection software. For the white box attack, the detection accuracy also increases for both datasets, but more so for the Batidol set than the WADI set. And for the black box attack, the detection accuracy is higher with less constraints in the WADI dataset than the Batidol dataset. However, in both cases, the detection accuracy increases as more constraints are added for the attacker. Other attacks that were discussed include the availability attack, in which an attacker attempts to decrease the detection accuracy to 0. The attacker picks a sensor to manipulate, making the system defender check the reading. However, the actual reading is correct, which decreases confidence in the detection system, and the detection software becomes less reliable. Another attack that was monitored was a real-time evasion attack to test real-time results. In this model, 15 hours of operations were recorded, and during the attack phase, all instances of anomalies were hidden. This was successful because the attacker was able to hide itself completely from the defender. To sum up the results, the authors found that the replay attack method was only efficient when all sensor readings are replayed, which is what we saw in the case of the unconstrained attack. Therefore, if a replay attacker does not have access to all sensors in the system, this will not be a viable solution for hiding anomalies, and the attacker will be found by the detection software. In the case of the white box attack, it was found to generate readings consistent with non-manipulated readings, making this a viable solution for hiding anomalies. Finally, with the case of the black box attack, this was found to also generate readings consistent with non-manipulated readings. However, it requires the alteration of a large set of data due to the requirement of the learning phase within the attack. So between the white box and black box attack, both are viable solutions. However, if an attacker wants to begin attacking immediately, the white box will be more viable because they will not have to rely on the learning phase of the black box attack. The main conclusions from the results are that a successful attack requires manipulation of certain physical constraints as well as real-time sensor readings. It was also revealed that manipulations can occur in real time when previously manipulations were mostly performed offline against a dataset before executing an attack. The evaluation has also revealed that future detection systems will require accurate detection of both unconcealed and concealed attacks to appropriately protect a cyber-physical system. There is a lot of future work that should be considered with this research. Some future work is to use machine learning to detect adversarial machine learning attacks. Now that the authors have demonstrated how these adversarial machine learning attacks can occur, researchers can benefit from this knowledge to use machine learning methods to sniff out these attacks and prevent them from occurring. The authors have also revealed the reality of adversarial machine learning attacks, giving other researchers the opportunity to further study these attacks and strengthen security in cyber-physical systems. Researchers also have the opportunity to explore physical devices that are more secure to prevent an attacker from loading adversarial machine learning software in the first place. The main conclusions from this paper are that understanding the potential of adversarial machine learning attacks will help future systems prevent such attacks. It is important to understand the difference between an adversarial machine learning attack and normal system operations. The physical aspects of the system must be monitored closely and possibly with sensors outside the network to verify an attacker is not passing expected data while an attack is occurring. It is still apparent that cyber-physical systems are at a large risk for attacks, and research must continue to protect these systems. Thank you for watching the video. Now you understand different types of adversarial machine learning and how it affects cyber-physical systems. We learned about the different types of attacks that can affect cyber-physical systems, how they occur, and how they manipulate data, and how this information can be used to create better security methods throughout cyber-physical systems. Thank you for your time.